I'd like you to write the mass action expressions in terms of concentration for the reactions in numbers 1 and 2. And then I would like you to write the mass action expression in terms of pressures for this one at the bottom. Okay, so Kc or Keqs for the top two, and give me a Kp for the bottom one, and we'll go over it. I'm gonna start writing it on the board. All right, let's do it. So for this top one, remember, mass action expressions are products over reactants. So product concentration raised to its power, since that, or raised to its coefficient, since that's got a coefficient of 1, you don't have to put anything up there. Then we got this guy, CO, that's got a coefficient of 1, you don't have to put anything up there. And then the H2, that's got a coefficient of 2, so we're going to square that. So there's the mass action expression for that top reaction. Now let's do this bottom reaction here. That's going to be Kc equals, going to be the NH3 concentration to the first power times the hydrogen sulfide gas concentration to the first power divided by the ammonium hydrogen sulfide to the first power. So those are your mass action expressions. Remember, the coefficients become the exponents, and it is products over reactants. Now, we said that you can plug in partial pressures instead of molarities and get an equilibrium pressure constant. And we said there is an equation that allows you to convert between equilibrium concentration constant and pressure constant. You do have to make sure that you're plugging those partial pressures in atmospheres. Anyway, so this is going to be Kp equals the partial pressure of CO2 cubed times the partial pressure of CF4 cubed divided by the partial pressure of COF2, and that's to the 6th. So there's our values for Kp. We put parentheses around the partial pressures if they have an exponent. If one of these things only had an exponent of 1, then you would not need to do the parentheses around it. Okay, but convention is we put the parentheses around it. Let's talk about what these values tell us. If we get an equilibrium constant that's really, really, really big, okay, much greater than 1, we define that as about greater than 1,000, then that means the product side is favored, right? Remember, at the end of the day, these values are product concentrations divided by reactant concentrations. So just think about it. If I get if I plug the equilibrium concentrations in, and I get a constant that's really big, that means I have more product than reactant. Okay, if I get an equilibrium constant that's really small, much, much smaller than 1, something smaller than 0.001, or 1 divided by 1,000, then the reactant side is heavily favored. There would be almost no product. And finally, if I get an equilibrium constant of 1 or close to 1, then that would mean the reaction goes about halfway before it reaches that dynamic state of equilibrium. Yeah. So remembering what those values mean. Okay, let's practice computing one. And I actually want to compute a Kp. Okay, so I'm going to solve for a equilibrium pressure constant. So if I give you the equilibrium partial pressures, can you turn that into an equilibrium pressure constant? So let's take a look at that problem. And before we get started on this problem, I want to remind you that I don't really care about this equation too much, but I do need you to know that you can go back and forth between equilibrium concentration constants and pressure constants, and that they are related by a factor of R. Why is that important? Let me tell you why that's important. Because R is 0.08206 atmospheres times liters over moles times Kelvin. Your partial pressures when calculating a Kp have got to be in atmospheres. So I want you to do 2 things for me here. Well, really 3 things for me here, folks. First thing, here's the reaction. I would like you to write a mass action Kp expression for this. Then you're going to need to convert these pressures from torr to atmospheres. What's the conversion factor? 1 atmosphere is 760 torr, and a torr is the same thing as a millimeter of mercury, right? So you need to convert those to atmospheres. Then once these are in atmospheres, I want you to plug them into the mass action expression and actually solve for Kp. Okay, so this is like our warm-up practice problem before we start getting into the heavier stuff. So mass action expression in terms of pressure, convert those partial pressures into ATM, plug them in, get me a Kp value, please. All right, I got 28.6. So first thing, you got to divide these all by 760. I got 0.155 atmospheres for NO, 0.232 atmospheres for bromine and monoatomic bromine, and 0.399 atmospheres for NOBr. And then I wrote the Kp expression, partial pressure of NOBr squared divided by partial pressure of NO squared times partial pressure of bromine. You know, you watch out. When I punch this in my calculator, I don't do any of those parentheses. I just do that to keep it looking clean. The only parentheses I enter when I put in my calculator are actually those parentheses. If you want to put it in one shot, right? Unless you got one of them fancy calculators, got the fraction line in or whatever. Just make sure you're getting 28.6. What does this tell us about the reaction? Well, it tells us that the product side is very, very, very slightly favored, right? I mean, that's really close to 1. Remember, greater than 1,000 means your product side is substantially favored. That is not greater than 1,000. So we are greater than 1, and when we're not greater than 1,000, we gonna have some of everything in there. And if you look, it's true, right? Look at these equilibrium partial pressures. There's a significant amount. They're all comparable amounts, right? Whether they're reactants or products. So it kind of makes sense, you know, that we get that value like that, or that value makes sense when we look at the data. Cool. All right. Let's do another easy one just to get warmed up here, folks. This time a little bit different. This time I'm giving you the equilibrium constant. I'm telling you it's 50.2. I'm giving you 2 of the equilibrium concentrations. I'm telling you the equilibrium concentration of hydrogen, 0.04855 molar, and the equilibrium concentration of iodine, 0.0468 molar. And I would like you to solve for the equilibrium concentration HI. Go ahead, folks. You got this. Stay organized. It always starts by writing a mass action expression and then writing down what you got, where you can go. So first thing we're going to do, these are concentrations. This is a Kc or Keq. We got mass action expression where it's the concentration of HI squared divided by the concentration of H2 times the concentration of I2, just like that. Now we go on, essentially call this X, right? So the equilibrium constant 50.2 equals X squared over 0.04855 times 0.0468. I'm sure you guys are appreciating the fact we don't have to worry about units. It's like the only time in chemistry where we don't have to worry about the units, right? You know us chemists. We are picky folk, but here the units don't have a physical meaning, so we can ignore them, and it's pretty awesome. So I'm going to multiply both sides by 0.002272. And we get 0.114 equals x squared, and now we just need to take the square root of that. And we get that X equals 0.338 molar. The equilibrium concentration of HI must be 0.338 molar. That's beautiful. You can kind of check your work here, folks. Now that I know that this is 0.338, now I could plug these values into the mass action expression, and I should get 50.2. So we can do that. Let's check our work. It's going to be 0.338 squared divided by the quantity 0.04855 times 0.0468, and we get 50.3 with rounding close enough, 50.2. There it is. This is a little different, right, than what we were doing, but we're still dealing with equilibrium concentrations. So what we're about to do tonight is I'm actually going to give you the initial concentrations, and then we can get the equilibrium. But for now, you've been given the equilibrium concentrations and the constant, and you were just looking for another equilibrium concentration. So it's kind of the same problem. Just instead of solving for Kc, you just solve for one of those things. How'd that go? Hopefully good. Hopefully that's going good. All right. And let's do another one here. One more, I think. Hang on, yeah, this is our last warm-up problem for the night. Okay, so the last easy one for all of tonight. Okay, it's about to get crazy. This time we're going to do essentially the same thing, but with KPs. So I'm giving you the equilibrium pressure constant, 2,910. And I would like you to solve for this missing partial pressure if here are the other partial pressures. Be careful. Remember, you got to be in atmospheres. You got this, folks. Go ahead. All right. If you're not done, keep on working. I'm going to go ahead and get started. I'm going to start by writing my mass action expression. I'm then going to turn those into atmospheres by dividing by 760. We get 1.78 times 10 to the negative fifth. What are the units on that? Well, it's going to be atmospheres, right? We just solved for the partial pressure of SO2Cl2. And we got 1.78 times 10 to the negative fifth. You can check your answer. Do 0.154 times 0.336 divided by that new one and see if you get 2,910. Let's check. We got 2,910. That totally works. There is your individual partial pressure. So these are easy problems. Why are they easy problems? Because you're being given equilibrium values, okay, and asked to solve for a constant, or you're being given the equilibrium constant and all but one of the equilibrium values and asked to solve for the remaining one. So these are just algebra, like easy algebra 1 problems, right?